All right, folks, let's start. This is Dr. Yuzo, ECE 360 Control System class. And this is our 12th lecture today. And can you guys hear me well? And being able to see my screen too? All right, thank you, Noah. All right, then we're gonna go ahead. So first of all, as I said at the beginning, by the end of last lecture, actually, we had 2 more examples for module 4. The time response, and 6 and 7. And has anyone done this and you want to check your answers? So the example 6, if you haven't done this yet, let me ask, given the problem like this, what do you need to do first? Anyone realize this? Anyone recall what we have learned? Anyone, any idea? Block algebra, very good. Sawyer got the point. Block algebra is for what? What the block algebra for? You can speak up.
Find the transfer function.
Find transfer function. Very good. Very good. Very, very good. So what we do here is, first of all, you need to recall that one fact here. Okay? No matter what we have discussed in this module, we're discussing this, right? Everything is derived out of here. TPTS, overshoot TR, steady state value, everything out of here. However, never forget this guy, first of all, is the closed loop transfer function of the system. So no matter what is given in the problem, if it is not closed loop transfer function yet, we need to find closed loop transfer function first. Okay, so first step is find closed loop transfer function. Okay. First step is to find closed loop transfer function if it is not given yet. That's why Sawyer told us to do the block algebra first. And according to which, what is the closed loop transfer function of this guy? Is this right? This is a closed loop transfer function, right? This closed loop transfer function. And if you further derive it, you got this result as the closed loop transfer function. Okay, this is the first step. With this, we start to find what? K, omega n, and the zeta, 3 parameters. And based on which we go ahead to find these values. Right? So from here, we try to derive because we understand this guy in our head is just equal to k times omega n squared, s squared plus 5s plus 25. And also we notice that what? Coefficient of s squared is 1. Nice. We don't need to do anything. Directly we derive what? So k times omega n squared in the numerator is equal to 25. And then 2 zeta omega n equals to 5. Omega n squared equals to itself is equals to 25. 3 unknowns, 3 equations. Done. K, omega n, and zeta. Of course, here from omega n squared equals to 25, omega n equals to mathematically positive and negative 5, right? However, omega n cannot be negative value. So it is equals to 5. Therefore, k equals to 1. Zeta equals to 0.5. Based on which we need to do what? We need to go back to the notes to find these formulas in terms of the omega n and zeta, TP, overshoot, and TS. So based on those, you got the values. And the correct values, once again, no one wants to try your answers. Anyone got the values? Yep, I'm seeing 2. You can speak up.
I got 0.73 second for TP.
Point what?
73.
0.73. Good. I got a 0.726, but yep, you go ahead. Anything more? Right, if no more than this is TS, and then 16.3% of overshoot. And then the last one is the rising time. The last one is rising time. So what do you need? Anyone remember? What do we need to find the rising time? Anyone remember what we need to do?
We need that table.
We need that table, exactly right. And from table, we locate what?
0.5.
0.5, exactly. Locate the zeta. And then correspondingly, at this particular zeta, we find what so-called normalized rise time, which is equal to TR times omega n, right? Which is equal to 1.638, right? 1.638, and then go back to here. And then normalized rising time equals to 1.638. Then further we got 0.328 seconds. 1, 2, 3, 4, 4 answers. Okay. This is the example 6. The next example 7. So is nicely seeing the given transfer function. This guy is directly the closed loop transfer function, right? And then find everything. Everything, it means the same these values. Oh, by the way, here, the steady state value. Anyone knows what is steady state value of this example 6? Steady state value is what? Anyone remember how to find the steady state value? It equals to what? Any memory? Okay, very good. Steady state value equals to 1 because steady state value is simply equals to the constant gain k. So as long as you derive the k value here, you know this is nothing but steady state value. So this is so-called everything: steady state value, TP, TS, TR, and OS. Doing all of these over, for example, 7 problem. So what we have is, once again, first of all, the closed loop transfer function is given as this, nice. And then what do we see? non-unity coefficient of s squared in the denominator. So this is obviously not okay, right? So obviously this is not okay. So closed loop transfer function need to be reorganized by doing what? By dividing by 2 on both numerator and denominator. And once we reach here, we go ahead and we know. Now this is 1. Coefficient is now 1 here. So we know k times omega n squared equals to the numerator 5. 2 zeta omega n is equals to denominator 2. Coefficient of the s here. Omega n squared is equals to 3.5. So from here, we got 3 values. There respectively are 1.43, 1.87, 0.535. Right? And then we immediately, once again, this is what? Steady state value we just mentioned. Then use the same formulas. You got TP, TS, and overshoot, respectively. TP turned out to be anyone? Anyone have any value? Any value here? And TS, overshoot, etc. There. Kevin got, yeah, 2 seconds. Yeah, Kevin is right. Just 2 seconds. 1.898, just 2 seconds. And TS, yes, what do we got? Yes, is 4 seconds. Overshoot 13.68. And then at this particular zeta, 1.87. Oh, I'm sorry. That doesn't make any sense. Obviously, this makes no sense. Omega n equals to 0.535. Okay, zeta is 0.535. Okay, this is 2 numbers. I had a typo here. Zeta obviously should be less than 1. Otherwise, it's not even a underdamped. It's not even underdamped. Omega n is 1.87. Okay, omega n is 1.87. So at this particular zeta, 0.535, you go ahead to the table, find the normalized resting time equals to 1.7. Then you are going to find the resting time equals to eventually 0.91 second. Any questions regarding at least the procedure, the idea? Any questions? We learned last Wednesday, and then if you guys don't review what we learned during the weekend, well, probably you don't understand what I'm talking about now. However, luckily we have recorded lectures, so go back to them and then review at least the majority of the lecture, and then you know what's going on here and why and how. Okay. This is example 6 and 7. But once again, okay, review what we have learned and do exercise I recommended. Okay, that's the best way and also the easiest way for you to prepare the exams and do well in my classes. Now, this is the Gantt chart we have. We are here at this particular cell, October 12th, or the 12th lecture. Also, the first lecture for module 5, the new module, steady state errors. The steady state errors. Right here. So, module 5, steady state errors. So first of all, we need to understand what this module is about. What this module is about. Trying to evaluate a system. Output steady state value. Output steady state value. Module 4, as you remember, was about the output waveform, including the transient part as well as the steady state value. Right? What does the output time response look like? And today we're going to talk about the steady state value. How good is the steady state value? Is it good or bad? And how to tell? Once again, we are using this generic control system block diagram. You all know this is input, this is output. This should be very clear now. This module 5 is studying where? It's not studying any block transfer function. It's studying one signal. So where is the signal? It's the error signal. And where is the error signal? It's here. This is the error signal. Output of the summing junction, also the input of the controller. We're studying this particular signal. We're studying this particular signal. Capital letter, of course, in S domain. And here, we need to talk about module 7 is the controller or say control system design module. However, this is number 5. We are approaching to there. So we start to talk about a little by little, gradually, the concept of the design. The first design idea is you need to understand what is the most important thing to worry about, to take care. Here I'm listing the so-called priority of the design. I'm giving the line with arrow here, indicating the priority, what? Descending order. So who is, in other words, who is the most important thing? The number one thing we need to worry about is that what? The system stability. In other words, if the system is not even stable, we don't need to talk about steady state error. We don't need to talk about a transient either. Okay? This is meaningless. I remember I had a similar conversation with John in previous lectures as well. Okay, so stability is number one. You need to first of all guarantee the system is stable, and then okay, you go ahead to talk about the steady state error. Steady state error means what? Steady state error means module 5, which further, of course, means in detail. They're talking about input dependent steady state value performance. And further, you will see we are studying this particular signal in the system, E of S. However, the steady state error we are looking for is not the frequency domain, E of S, but time domain, E of t equals to infinity. And this is eventually the one we are talking about, steady state error. Okay. We will see this further, but here, just listed here. Okay. And this is the one we are studying in this module, okay? Not the frequency domain. Okay. Stable, okay, we go ahead to see the steady state value performance. Very nice, okay. Further, we go to the transient performance. In other words, if the system is stable, but the steady state error is terrible, which means your steady state value performance is poor, guess what? Don't even think about the transient performance. Okay, it's meaningless. Okay, this is so-called the priority of design descending in order. Okay. Most important thing. Second one, last consideration. Okay. This is descending order. The transient performance, we actually have talked about quite a bit in module 4. Okay, time response, in where we study the is also input dependent. Okay, steady state value and transient performance, they all input dependence. The transient performance. Further, we are studying what? We're just studying the C of S, right? Output. And then from C of S, we can find the C of T. This is one thing. And also from the closed loop transfer function, we can find what? TP, TS, overshoot, TR. No matter it's a first order system or second order system, it doesn't matter, okay? The key is it must be closed loop transfer function. From other transfer function, no, we can't tell these details. Okay. And speaking of the closed loop transfer function, let's review a little bit this, okay? What is the closed loop transfer function of this guy? This generic, but this is the very best, the best example for us to review these transfer functions. Okay. You have also open loop transfer function, right? And what else transfer function we mentioned before? Anyone remember? Oh, closed loop, open loop, and what?
Feedback.
Feedback. What else? Last one here.
I don't know. Negative feedback, is that, or just
Say that again?
Feedback including both negative and positive feedback, right?
Yes, yes,
Okay.
yes, yes.
Forward and backward transfer function.
Well, yeah, that is correct. Okay, this is forward. Well, we don't have we don't have backwards. Okay, we don't have backward. Backwards are basically a feedback. So we have feedback and forward. Okay, forward transfer function. I'm emphasizing the very last one because this is the one we are using in this particular module 5. Okay, in this module 5. Okay, all right. Let's start to review. What is the closed loop transfer function of this guy? What is it? C times P over 1, what? Let's say this is a negative, positive, and then in the denominator here is a positive 90, right? What is it? C, P, what? H. Okay, good. This is the closed loop. Then what is the open loop then?
C time H.
Good. CPH. CPH. And who does feedback? Feedback is very easy, right? It's just H. Now, who is the forward transfer function? Once again, with this particular module 5 is using this particular transfer function. Forward, who is it? So you need to understand this very well. Who is it? Who is the forward transfer function in this system?
C time P, CP.
Very good. Okay, CP. Okay, just C times P. Okay. And once again, we're gonna use it. Okay, we're really gonna use it. We're really gonna use it. Okay. It's CP. Okay, so CP. Good. Very good. Okay. So, and then we go back to here. Okay, module 4 once again, transit, based on what? Closed loop transfer function. Okay. Not any other ones. Right. This module 5, we're gonna talk about the steady state value, and then it is also input independent, input dependent. And we are going to find the arrow signal here, this signal here in time domain, okay, when t is approaching to infinity. Okay, this so-called steady state error. But here, this one, let me tell you, is about module what? It's very easy to guess, right? Module 4, 5, what is the next number? Does that make sense? It's module 6. Module 6. And the more details gonna be instructed later on, okay? This is also kind of the structure of what you guys are learning. Okay? It's organized in a certain way. This is the kind of overall picture, and then let's go into here, and let's go into here in detail. First, what is steady state error? Steady state error. By its definition, or say the description is as simple as this. Just the difference between what? This is very easy to see, right? So this error signal is the difference between whom? Input and whom?
Feedback.
The feedback, right? Feedback. Well, the feedback might be the output directly if the feedback transfer function H is unity, right? But it will be more accurate if we just say input in between the input and feedback. Correct. And then this is the description. And then what we need to know is in frequency domain, or say the S domain, what is it? Just the E, capital E of S. And then by applying the inverse Laplace transform, we got the time domain. T domain, whatever you call it, is lowercase e of t. However, here, be very careful. It's not any t moment, but a particular t moment, which is infinity, as infinity. Okay? T equals to, or say, approaching to infinity. And then at that moment, what is the error signal? That's the steady state error. That's the definition for steady state error. So once again, this guy is the one we are talking about here. Okay, this is the steady state error. Looking for the system steady state error. What we are looking for? Not this guy, but this guy. This is the one. called the system status error. It's time domain result, not frequency domain result. And here we also need to recall a little bit, because once again, it is what? The input dependent, right? So who are the input signals we have learned? Impulse, step, ramp, and what? Parabolic. Impulse, step, ramp, and parabolic. 4 different input signals. We use them as well in the previous module. Okay, and we have what? We have a handout about them, right? We have the handout. And the Laplace transform table. That handout including all those 4 inputs in time domain and the frequency domain. Okay. Oh yeah, a little bit the output. And error. I list them in parallel to differentiate them easier. By applying inverse Laplace transform, we could get time domain result. And when the time approaching to infinity, what do you got? Respectively, what? Steady state value. This is what? Steady state error. Okay. So by placing them in parallel, you can tell the difference, or say differentiate them better. Okay. This concept must be very clear. The concept must be very clear. Okay. The concept must be clear. What we are talking about. What we are talking about. Now, with all of those being said, let's now start to really see how to find the values, okay? How to find the steady state error values. Okay. First case is what? So-called unity feedback system. A unity feedback system. Unity feedback system, what does it mean? H equals to 1. Makes sense. H equals to 1, what does it mean? Feedback signal is equals to output. Right? Just like here. H equals to 1, and then your feedback signal here just equals to the output signal. This is the unity feedback system. And then we start to look for the steady state error in time domain. Once again, time domain. And then what we can do is this. Okay. Once again, if we are using the this basic using this system, combining C and P together. Yeah, combining C and P together. Makes sense. This is the input, output. Therefore, this is output as well. This is the E. So in this system, what we have is, first of all, E of S equals to what? Input minus output, right? Input out minus output. And output equals to what? Output is the output of the G. So output equals to error signal times the transfer function G. And then you move this term to the right-hand side to combine with this E term, right? And you can find the E term equals to R over 1 plus G. Of course, I'm skipping parentheses of S, but you understand what I mean here. Okay? You have it or not, well, not a big deal. The key is, this is what? Input, right? What is this? G is what? What is G? Transfer function. Transfer function. But more importantly, this is what transfer function? Remember what I said? Forward transfer function is the one we're going to use in this particular model. Very good. It's a forward transfer function. It's a forward transfer function. So this is E equals to this. And then, of course, we could do something like this. We could do something like inverse Laplace transform to find E of t, right? And then from here, you go ahead to make the t equal to infinity. You got steady state error. No problem. This is, of course, 100% correct. However, here we're using something new. It's called final value theorem. Have you guys learned this before? Ever heard of it? Final value theorem. Ever heard of it? Sound familiar? Sounds familiar. Probably some math class ever taught this. Nope.
This doesn't have to do with like if S is 0, that's the steady state, or no?
Well, close. John's answer is very close. So obviously it has been taught before. Good. Anyways, the definition is like this, okay? The final value of a time domain function f of t is equals to what? As John just mentioned a little bit, is equals to the value of s times capital F of s in S domain when S is approaching to 0. Be very careful, okay? This lower f of t and capital F of s has a relationship. Okay, what's the relationship? Capital F of s is the Laplace transform result of lower f of t. Okay, so what does it mean? What this final value theorem is talking about? It's talking about in the time domain of functions, final value can be found what in the frequency domain. This is what it's for. This is what this is for. Without conducting what? Without conducting this Laplace transform, inverse Laplace transform. Without conducting this. All right. So according to this theorem, to find this guy based on this, what is the formula we should have? E infinity. This is nothing but the steady state error. This is a steady state error. Nothing but the thing we are looking for all the time. Steady state error. Right. Equals to what? According to this. Equals to what?
Well, S times f of 0.
The key is who is the f?
Oh, large E of 0.
What is that?
So if you're saying E to infinity of t, that should be equivalent to S times big E of S evaluated at S equals 0, right?
Yes, basically he is right. But first of all, is a limit. We are looking for this, right? So first of all, you need to understand that as approaching to 0, you need a limit. You're looking for a limitation. You're looking for a limitation. But Kevin is basically right too. Is basically right too. However, you don't want to write in that way. Maybe you see why. Okay, maybe you see why. Why Kevin's E of 0? We don't want to do that. Let's see why that. S approaching to 0 and then S times E of S. Correct. Okay, correct. And further is just equals to what? S times R over 1 plus G, right? Steady state error here. Of course, here is not in terms of H at all, because H is equals to 1. Now we are talking about a unity feedback system, okay, and unity feedback system only. This is the result. And that's the formula for it. If you see how to use it. If you see how to use it. And we move on to the next, which is here. Once again, never forget a steady state error is obviously what? Input dependent, right? It makes perfect sense. Your steady state error calculation formula is in terms of R, input, and the forward transfer function G. Perfect sense. Right? So the R, the input R of S maybe could be, because this is S domain, right? Input in S domain, like what? The impulse, the step, the ramp, parabolic, right? And let me ask you, who are these? I'm writing 3 the most commonly used input for this module. What are they? First, 1 over S. Who is it?
Yeah, impulse.
Uh,
All right, unit.
Step. Here we go. Noah is right. Okay, Noah is right. Okay. Unit step. It's not impulse. Okay, it's not impulse. Okay, by checking the handout, you will see it. It's not impulse. It's a unit step. By the way, why we call it unit step?
Because we're only putting 1 in
the numerator. Correct. Okay, so, or say the coefficient of this is 1. Who is this? What is it? This guy is unit ramp. And who is this? Unit parabolic. Okay. And the corresponding time domain function you could find from the handout. Okay, these are the 3 most commonly used inputs. We're gonna quite often apply them. Right. And with these inputs, let's see. Okay, let's see. With these inputs, here I place them here. Place them here, and then go ahead. Let's see what result we have. The system forward transfer function, which is G, just G here. Generally speaking, it could be organized into such format. Once again, okay, as a forward transfer function, a student make mistake on this very point too often. Just a too often. So you want to try to avoid that at the beginning. The GFS could be organized in this format. And this format is what kind of format? There's a name for it, right? That's called what? Zero pole transfer function, right? Zero pole transfer function. What does it mean by zero poles? In other words, who are the zeros? Who are the poles for this G? Who are the zeros?
Negative G1 and negative G2.
I know what you mean, but you need to read carefully. We are talking about zeros. So it's not G's, right? Or what? Who are the zeros?
I think he meant negative Z1 and negative.
Correct.
Z2.
Correct. It's negative Z1, negative Z2, and et cetera, et cetera. Those are the zeros. Okay. Maybe I here yeah, that I'm wrong, and he was talking about Z's, but it sounds like G to me. Anyways, zeros are negative Z1, negative Z2. Very good. Okay, so all of you guys realize it's negative. Okay, it's not positive. So who are the poles here? Negative P1, negative P2, and so on, right? So this is so-called zero pole format. This is actually what we learned before, but in this module, the point is here. Okay, the point is here. This guy. N's value is equals to the system type. Okay. This is one of the most important concepts we learned today. Okay. The value of n here, n is what? Is order of the S term, right? In order of the S term, right? The value of it is equal to system type. So system type might be 0, 1, 2, or 2 plus, right? Is it possibly be negative? Is it possible to be negative?
Well, if S was negative, it would be on
N
the
is negative.
numerator, so it wouldn't really matter, or it wouldn't be possible for you wouldn't have an input then at that point, right?
No, n is negative first. It's not S equals negative. N if is negative, then what happened? This S term won't appear in the denominator, but numerator, right? So here, remember the n's value, the n is the order of the s term in denominator. Okay, it has to be denominator. If it is in the numerator, then n equals 90 value, then that's not system type. No, that's not the correct concept. It must be in the denominator. It must be in denominator. Okay, is system type. Okay, it's system type. So let's take a look at these system types, see what we can see. Okay. When n equals to 0, say the 0 type system. Let's see what we're gonna have. But before that, let's add something here. You know, I want to try to differentiate the system type and another term also regarding the system, system order. We have learned the system order. It's a system type. What does it mean by system order? Anyone remember? First order system, second order system, right? We learned from module 4. So what do they mean? Anyone remember? Or say, how can we tell the system order? First order system, second order system. How can we know that?
Well, you have to take the transfer function, not the input transfer function, and if the denominator.
We don't have a input transfer function. What do you mean by that?
I guess I meant, sorry, not input transfer function. You have to take the input away from the g of s. It would be in this case. So g of s transfer function, whatever s squared, that squared term, the largest n, I guess in that case, would be the order of the system.
No, it's some
Order of system depend on the n value. Like if n is 1, that's first order.
which n? Where is the n?
S to the n, like a denominator.
And you mean the same n here or something different?
The same n value, I think, denote the system order.
No, not quite. Not quite. I'm expecting, I'm waiting for a better answer. Kevin's answer is highest power of s in denominator.
You are now
Denominator of what?
Of your g of s.
No, still not quite right. Still not quite right. All right, very good, very good. Find out a very important concept here then. Still waiting for the correct answer. Anyone? S after FOIL, what that mean, Vincent? What does that mean?
Like after you multiply all the different brackets, the parentheses.
Closer? No, the answer becomes closer. However, you need to divide that and then the what? From which, from where? From here? Is it from here? You divide them, you times into the parentheses and then come up with a polynomial.
Yeah.
Oh, no. No, not quite. No. No, the numerator highest order of s, no. That getting away. That's leaving away, Sawyer. Anyone else?
Would it be the entire system's transfer function instead of just the forward transfer
What
function?
do you mean by entire system
For-
transfer function?
take
We
the entire
never
system
talk about
trans-
the entire. Say that again.
If you look at the highest power of S in the denominator for the entire system's transfer function, like we just did, where we ignored the input and we looked at closed loop transfer function where we had G of S. and
I
the H-
think Kevin's answer now is the closest answer we could have. Yeah, maybe for this time being. Let me describe this once again. How to find a system order? Listen very carefully, everybody. First of all, what you need is closed loop transfer function. Okay. Kevin called it what the entire system transfer function. Well, obviously, closed loop transfer functions is better. It's a better description. First of all, we are talking about closed loop transfer function rather than the forward transfer function. Okay, this is a very important point. We are talking about a closed loop transfer function. From where you go to the denominator, polynomial also. Why I'm emphasizing the polynomial? Remember, Vincent just mentioned one very important point. The closed loop transfer function might look like a zero pole as well, right? This guy might look like in terms of this format as well. However, if you have S term in the denominator and the order of it is n, that n is not the system order yet. Because S and this n here is not order of the denominator polynomial yet. You need to times into it. It makes the denominator becomes a what? As certain order with certain coefficient in front of it, and times as k91, and then so on and so forth, right? So here, this k of the closed loop transfer function denominator polynomial is the system order. Okay. So in summary, the system order means in the closed loop transfer function denominator polynomial, the highest order of S is the system order. On the other hand, the system type here means, first of all, is forward transfer function. It's not closed loop transfer function. We are not talking about the same thing. And in the forward transfer function, you're looking for the denominator S term, which is not a polynomial highest order. Did I make myself clear? Is these two concepts now clear? Better? Anything? No feedback? All right, thank you, Vincent. All right, thank you, Noah. All right, thank you, Alex. All right, good, okay, good. And it won't be a surprise that this is one of our, maybe two of our multiple choice problem in the next exam. I won't be surprised. But hopefully you won't either. Anyways, now let's go ahead to take a look at the zero type system, and the steady state error. And according to the steady state error equation we derived previously, the S times R 1 plus G, right? let's study three different inputs, 3 different unit inputs. What is the steady state error? So here is equals to limitation s approaching to 0, and then you have s times what? 1 over s, right? And then plus g. And equals to s approaching to 0 and 1 over 1 plus g. From here, we can have some conclusion here, right? So according to this zero type system, so this is the steady state error formula we derived in previous page up here, right? Up here, and then here. And then to 3 different inputs, you have 3 different results here. So if the n equals 0 for n-type system, this steady state error is what? What do you think? How about is just equals to a constant? How about that? Does it make sense? Because there's g here, well, basically this is what? This is 1, right? As to the 0 is equals to 1. And then the g of s ends up with numerator bench of s first order s term product and divide by the first order s term product, and then you substitute s with 0, and then you end up with these zeros product divided by the post product. Right? Does it make sense? And then what if the ramp input to zeros type system? What are we going to have? S times 1 over s squared. Denominator is 1 plus g, and then equals to so approaching to 0, and the numerator is 1 over s. Denominator is 1 plus g. What this result is? What this result is? Anyone? Anyone?
If we add 0 to s, wouldn't that infinity over some particular number?
Which is equals to?
Infinite.
Correct.
So I'm just kind of wondering, like, because isn't g itself supposed to be a transfer function?
It is?
So what happens if the transfer function of g has something where the denominator is also g itself when evaluating 0 becomes infinite? Because then you get infinite.
No. We have never forget the roof, which is n equals 0. You understand what I mean? So here is 1. Does it make sense now? Do you plug the s equals 0 into here, and then it's just like you said, it equals to a certain constant value.
So that's why it's important to separate G of S from our input
Correct.
signal.
Well, separate from your input. What do you mean by that?
Well, I mean by separating the input and knowing that G of S is equal to N and for the step, ramp, and parabolic, that'll allow us to know that as long as the original G of S transfer function is 0 for N, we know that the limits will stay exactly the same. Because if N is 1, I'm assuming then that these limits that we're just writing down now won't hold or may not hold.
That's basically right, but you're understand. It's a little bit weird. Well, but it's basically correct. Okay. And this G here, the bottom line is just like John just mentioned, everybody. Right? The G here is G itself. Okay? Never involve your inputs yet. Okay? Never involve it. Let me talk about the system type. It's independent of the input. Does it make sense? The system type, this concept is independent. Independent of input. Okay. You're not involving the input yet. Okay, this concept. So here we are saying n equals 0. Okay, this is 0 type system. And then we're gonna definitely have such conclusion. And here, similarly, what are we gonna have? Anyone? So to parabolic input, the 0 type system gonna end up with what?
Infinity.
Infinity. Good. Yeah, that is right. Infinity again, for the same reason, right? For the same reason. And we're gonna be able to do what? One type system for 3 different input and the 2 type system with 3 different inputs once again, right? So on and so forth, so on and so forth. So this is the idea. This is the idea, and I will provide you a better summarized relationship between the system type and the steady state error. Okay, I'm gonna provide a better summary of so-called relationship between system type and steady state error. Okay, this summary I'm going to provide. Okay, maybe by next lecture. But the basic idea and how I derive that summary is presented here. Okay, you have a basic formula to follow, and then we know the system type as 0 or any other values, and then correspondingly we substitute s equals 0 into this limitation. Once again, different inputs give you different steady state error. Therefore, we said at the beginning of the lecture today that steady state error, like the steady state output value, They are what? Input dependent. Input dependent. However, never messed up the system type concept, which is what? Independent of the input. No matter what input is, we are talking about a system type, which supposed to be input dependent, right? And that makes perfect sense, actually, right? So this is the things we learned today. And at the beginning of the next lecture, I'm gonna present the summary between the system type and the steady state error, and followed by examples. Maybe you'll be able to find the calculation there. Okay. Since these concepts are very, very important, let's go back to here for maybe another 5 minutes. Take a look, folks, and see any questions. Never mess them up. Never mess them up. Okay. System order. What does it mean? It means closed loop transfer function. System type is found based on the forward transfer function. They're not even talking about the same thing. Okay. And the poles and zeros of a system. So you can imagine in future, given a system a forward transfer function, you need to somehow what? Find out the S term, right? S term. For example, let's say this. Giving away a G of S forward transfer function, which is equals to what? 3s3 plus 2s2 plus S. And the numerator might be whatever I give you. What is this? What is the system order? System type. System type is what? What is it?
Well, we can pull out at least an S.
Mm-hmm. So
the system type would be since at least S is now to the first power, it should be a 1-type system, right?
good. In other words, following John's idea, we need to pull out the S, and S with order of 1 is the highest that you are able to pull out, right? And then we end up with S cube 3s squared plus 2s and then plus 1. You see what I'm saying? Type 1. The order of S here is 1. Right? Order of S here is 1. That's why it is type 1 system. And type 1 system gonna end up with what kind of steady state error? For obviously we have 3, right? Generally speaking, have 3. I mean, correspond to different step, ramp, and the parabolic equals to what, and what, right? These are the things we can learn from next lecture. However, from here you can tell the basic structure and idea.
So if you were to ask us, okay, now what's the system order? That would be a trick question. We can't answer that, right?
Exactly right.
Because we're given the
why you can't answer
function, right?
Why you? I'm sorry. Why you can't answer that yet?
Because we don't know. For one, what kind of? I mean, we guess we can assume that there's a feedback loop, but we don't know if it's negative. We don't know.
Exactly right. Okay.
And
Is everybody following?
The system order with closed loop transfer function, it has to be closed loop transfer function. It can't be open loop transfer function.
No. Closed loop is closed loop. Open loop is open loop. it is closed loop, then definitely it won't be open loop. Yes.
But if it is if the system is, say, open loop, then the transfer function would be the open loop, or no?
The system is open loop system, which means you don't have a feedback like this.
Yeah, they just multiply.
This guy. You
Yeah.
don't have a closed loop. Right? You don't have a closed loop. And then what is the closed loop transfer function? What's the open loop transfer function of this guy? Say this is G1, G2. What is it?
The
Closed loop transfer function. Well, it doesn't have a feedback. It doesn't have a closed loop. But well, the closed loop transfer function is basically means the system total transfer function. Okay. As Kevin's idea about that was actually correct. Okay. System total transfer function is nothing but closed loop transfer function. They refer to that. No problem. So, and based on that idea is what? Just a G1 times G2. And then what is the open loop transfer function? Open
G1.
loop transfer function, same thing.
Okay, and then that we would consider to be our system, the entire system's transfer function, right?
Correct.
Okay.
All is the entire system transfer function. No problem. This concept is correct. Yes, the entire system transfer function means nothing but the closed loop transfer function. You have a feedback closed loop. Then you do. You don't have one like this. Then well, nothing wrong with the definition. Still, the definition remains same. The total system transfer function. G1 times G2.
Now, the system order now and system type, would they be the exact same? I guess, because that
Yes. Definition wise, correct. However, you're never gonna come across that scenario, right? You don't have even a feedback here. This system, 9 out of 10 won't work. Won't work yet. Any other questions, concerns? All right, thank you for attending today's lecture, and talk to you guys on Wednesday. Once again, please remember to review whatever we have learned before. We learned something, well, not something. Almost everything we learned in every lecture is new to you guys, okay? So don't have any doubt about this. Just this is electrical engineering. The major course is just like this. Every lecture is talking about something you never heard before. Very, very likely so. So something new means if you don't review it right after, guess what? Second day, you only remember 50%. The following day, you only remember 50% of the previous day, which is 50% of the original. So 50% times 50% times 50%, and then times 50% equals to what left in your mind when you attend next lecture. See how terrible we are, right? So you have to review, okay? Remember to review, okay? See, maybe just the 10 to 15 minutes, go over all of the notes. That might be enough, actually. At least you understand what I'm going to talk about, right? So remember to do so. You don't want to wait or accumulate until a couple of days right before the exam. Well, that's going to become disaster. And also, whatever I have reviewed in my review lecture means nothing to you. Okay, because you didn't understand what I'm talking about. Okay, that's absolutely disaster. Okay. You won't be able to fully utilize my review either. Absolutely not. Okay. Anyways, my office hour right after now. So go to the Teams to read me out if any questions. Okay. Thank you again, and see you guys later. Thank you guys. Bye.